Hello and welcome to the Maths 2 component of the online BSc program on data science and programming. This video is about Riemann sums and the integral. So let's recall what we did in the previous video. In the previous video we computed areas, and the underlying theme over there was that if you have an arbitrary shape, then you try to approximate it as well as you can by rectangles. You keep dividing and dividing and dividing, making smaller and smaller rectangles, and hopefully you will cover the shape entirely. And as you take smaller and smaller rectangles, in the limit the sum of the areas underlying those rectangles will give you the shape of the area of the shape under consideration. So there were different ways, of course. Sometimes we, instead of rectangles, we use polygons or trapeziums or triangles, so other shapes which were all derived from the rectangle. So the rectangle was our basic building block. So let's make that precise. So here's a strategy to compute areas. Suppose you want to compute the area of a given shape. Break the shape you have into rectangles. Some part of the shape may be left out, some extra part may get included. So we saw this in the previous video. Calculate the area covered by the rectangles. Decrease the sizes of the rectangles used. The part of the shape that gets left out and the extra part that is added in, these keep decreasing because you are taking smaller and smaller rectangles, so you can approximate your shape better. And then each time you do this, you recalculate the area, and as the sizes decrease, the area of the shape is better and better approximated. So in the limit you will get the shape of the area of the shape. So we are going to use this strategy in a sort of coherent fashion, and we are going to talk about the area under the graph of a function. So here's an example of the function y is equal to e to the power minus x. So let's say I want to approximate the area under the graph. So suppose, let's say I want to get this area over here. Let's say I want to get this area over here between minus 2 and 2. So in other courses you may have come across this notion where the computing this area was important, particularly in statistics, which you either have already seen or will see soon. And so we want to know how to go about doing this. So here's the area I want to compute. So one strategy for doing this is to approximate this by rectangles. What kind of rectangles do we take? So here's one idea about what kind of rectangles to take. So we could choose rectangles like this. So here's minus 2. So I choose a rectangle like this. I choose a rectangle like this, and then this, then here, 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 here. Yeah, you can see what I am doing. Okay, right. So you take this set of rectangles, you compute its area, and then what do? You shrink these intervals and take smaller and smaller rectangles. And you can see that if you take small enough rectangles, this area that you want, which is in green, you can get it as you can approximate it as well as you want. And in the limit, meaning if you keep doing this process and allow your rectangles to get smaller and smaller and smaller, then you are likely to actually compute the area over here. So you could use this strategy for any graph. So here in particular we are doing it for y is e to the power minus x between minus 2 and 2. Okay, so this process was sort of formally introduced in the 1800s or 1900s, and there is a name for these kinds of sums. They are called Riemann sums. So I am going to describe whatever I did in our previous slide in a more mathematical way. So let f be a function from the domain D to the real line. Suppose the interval a comma b is in the domain D. So that means the function f is defined on the interval a comma b. So let P consist of the following data. So P is here, P is supposed to be for partition along with some other data. So partition of a comma b So that means the choice of intermediate points is x0 less than x1 less than dot 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 up to xn, which is b. Okay, so in our previous picture, these things that I have drawn here, this would be your x0, this first thing would be x1, x2, x3 all the way up to xn, which was 2, and x0 is minus 2. Okay. So this is a partition of your interval a comma b. You could choose your partition so that it's uniform, meaning the distance between x0 and x1 is the same as x1 and x2, x2 and x3, and so on. Or you may choose an arbitrary partition. So along with this partition, you also want to choose for each small interval that is contained in the partition. So xi minus 1 to xi, you choose some number xi star from that interval. Okay, this is the data p. Okay, so let's repeat what we are doing. We are taking a function f which we know takes values on the interval a comma b. It's defined on the interval a comma b, and then we are dividing a comma b into n parts, and then in each of these parts we are choosing a point. This is what we have done so far. Define delta xi to be xi minus 1. That means the length of the ith piece. That's what delta xi is. And this thing which we'll call it norm of p. So these two lines with a p and then two more lines. Let's call it norm of p. And this is just a name for now. Don't bother too much about what it means. So let's call it. So that let's define that as the maximum of these delta xi's. So in particular, if you choose all your lengths to be the same, then this will be just that number. So in your previous picture, the delta x1 is this distance here, this distance here, and delta x2 is this distance here, etc., and delta xn is this distance here. So at least the way I have drawn it, it's not the same. So your norm p will be the maximum amongst these distances. Okay, so that's what delta xi and norm p are. The Riemann sum of f with respect to the above data is defined as, so you have your data p, which consists of a partition and a choice of point corresponding to each small interval in that partition. Then we define the Riemann sum corresponding to this p. So S of p is summation f of xi star times delta xi. Okay, what is going on here? So let's go back to our picture over there. So suppose I choose my xi star to be the first point of that interval, right? So xi star is, suppose I choose xi star to be, so xi star is xi minus 1, right? Xi star has to be between xi minus 1 and xi. So I choose xi star to be xi minus 1. Then what do I get? I get x naught times, sorry, f of x naught times x1 minus x0. What is that? That is exactly the area of the first rectangle over here, right? That's the area over here, this area. That's what is f of x naught times x1 minus x naught. What is the second one? So the second one is f of x1 times x2 minus x1. That is exactly the second area. So it is this second area here. Yeah. So what we are doing is, if we had chosen xi star to be xi minus 1 and we had that that p over there, then the Riemann sum is exactly the area that we have the sum of the rectangles. So what this is doing is, it's saying you take your interval xi minus 1 to xi. Over that you take the rectangle of height or breadth f of xi star. Okay, and then when you multiply the length and the breadth, so the length is delta xi, the breadth is f of xi star, you get the area of that rectangle, and then you sum up all these areas. So that's an approximation for your the area under the graph. So that's the idea of what's going on. So that's a Riemann sum, and of course what we would like is that we keep refining our partitions. So this P is going to now start changing. So we will take smaller and smaller P's, and that will give us something interesting. So let's go to GeoGebra and do some computation. So I got this from the GeoGebra website. So here's a function. This is the function sine of 2x minus x squared by 10 plus 3, somewhat complicated looking function. And let's plot all these various sums that we have. So these are the Riemann sums corresponding to different choices of xi star. So here is the left hand sum. So we want to approximate, we want to compute this between 1 and 5. So between 1 and 5, let's say we have the number of intervals is 5, and we are taking equidistant intervals. So that means delta xi is 5 minus 1 divided by 5, so 4 by 5. So here your first, that's 0.8. So your first interval is 1 to 1.8. Your second interval is 1.8 to 2.6, then 2.6 to 3.4, and so on. Okay. And now what we have here is our left hand sum. What that means is xi star is the left endpoint of your interval. So xi star is xi minus 1, which is what we had in our previous example for e to the power minus x. So in that case, this is the picture we get, and you can see here the value of the left hand sum, it's 9.53 units. So this is the Riemann sum corresponding to xi star equals xi minus 1, and xi equals 1 plus I times 0.8, and there are 5 intervals. And now we can play this animation. If we play this animation, then the number of intervals increases, and you can see what happens. Yeah, your intervals shrink, the number of rectangles increase, and slowly you are starting to approximate the area under the graph better than the previous one. So this is now 8.83 units. Yeah, you can see it's changing, the area is changing. So the area is occurring in this panel on the left, where you have the left hand sum. And what is the 2 area? Well, it's 8.08 square units, and as you go on, it's going to get better and better. Of course, it may not get better immediately, but in the long run you would expect that it gets better. Okay. So this is with a choice of xi star equals xi minus 1. Instead you could choose xi star equals xi plus 1. In that case, you get a different set of intervals, you get a different set of rectangles, and this is how those rectangles look like. And now if we play this, let's see what happens. So let's start with just one rectangle. So you can see if you have one rectangle, this area is actually negative, so it's minus 0.176 square units, very far from the actual value. But now as you do better, meaning you start using more and more rectangles, which is to say finer and finer intervals, you can see it starts becoming better and better. So it's 7.42, 7.47, 7.6, and slowly it's going to come closer and closer. So if I had played this till say n is 500, you would have seen it's very close. Okay. So here xi star was chosen to be xi. So remember, xi star was any point between xi minus 1 and xi. It was a particular choice. Here we made the choice xi star is xi. Yeah. So the right hand sum. Instead you could have the midpoint sum, let's say, and if you take the midpoint sum, what do we mean by midpoint sum? We mean you take xi star to be xi minus 1 plus xi divided by 2. So if you do that, let's play what happens. So right at the start it's fairly close, so it's 7.28 units, square units, and you can see slowly it's better and better approximating. So it's now 8.09 square units. 8.08 square units, which is precisely where we are. Yeah, and you can see it's a really good approximation if you look at the picture. Okay, so that's the midpoint sum. Now I have defined the Riemann sum with the data, which is you choose an interval and a point in that interval. Instead, sometimes you could choose a slightly different set of data. You choose your partition, but then instead of choosing xi star, you could choose, for example, say the largest value of f of x between xi minus 1 and xi. Yeah. So, if you choose that, is called the upper sum. So, that is always going to overestimate your area. So, here's the upper sum. So, as you can see, the chosen number to multiply by is the maximum of f of x within that interval. Okay. And if you play this in the initial stage, it is really large, but slowly it is better and better, going to get approximated better and better. And it is an upper bound, remember, because it is always going to be larger, but in the limit it will come closer and closer, and that is what we saw. Okay. And this idea is very similar to the idea that we saw for the way Archimedes got to the area of the circle. So, he got overestimates based on polygons, and then he got underestimates based on polygons, and then he said it should be between these two, but in the limit both of them are pi r squared, hence it must be pi r squared. So, you can overestimate by the upper sum, then try to take the limit, or you can underestimate by the lower sum. So, here instead of taking maximum, you take the minimum, and again let us play this and see what happens. So, when you take the minimum, the starting place is you are in really bad shape, because the minimum is actually a negative number, but if you keep going, then slowly it is going to get better and better, and you can see the numbers here at 6.98, 7.05. The picture tells you already what is happening. So, this is a underestimate for the area, and the true area is going to be between the upper sum and the lower sum. So, in the limit, if upper sum and lower sum go to the same value, then that is going to be the area. Okay. And then one last example of another thing you could do, you could use something called the trapezoidal rule. So, you may have you may have seen this at some point in school. We have something called the trapezoidal rule to estimate areas, and the idea is exactly what we have here. So, instead of taking rectangles, you take trapeziums, and here is how you do that. So, here is now various trapeziums. So, what you do is you have xi minus 1 and xi, and now you join f of xi minus 1 to f of xi. So, it is a right angle trapezium at the base, and then at the top it is like this. And there is an important takeaway for why we want to do this. You see, we could, instead of doing this, we could take a line slightly above, and we could use something called the tangent, right. So, and if we did that, well, that would also be an approximation, and then that may give us something interesting. So, keep that idea in mind. It is going to come up in the next video. Okay. So, coming back to the trapezoidal rule, you are estimating your areas using trapeziums. So, this is actually a much better approximation as compared to the others, and if we play this further, you can see it is very close, 8.06, 8.07, 8.07, and it is going to remain over there. So, fairly close to 8.08. Okay, and you can see in the picture also that it is really well approximated. Okay. So, I hope the idea of Riemann sums is clear. So, we are going to use Riemann sums based on the rectangles, but you could have other kinds of Riemann sums, and it will not matter if your function is what is called Riemann integrable. It does not matter really what kind of Riemann sum you take. In the limit, they all give you the same thing, which is the area. Fine. Now, I used several words there. I used the word integrable, I used the word integral already, and the title of the video had the word integral. So, let us go to what the integral is. Before that, let us stop for a second and ask two questions. One is, well, over here I said this is the true area. How do I know this is the true area? How did I compute this 8.08 square units? Yeah, so that in itself is a question. So we will of course aim to answer that question shortly, not this video but in the next video. And then there was something here called show integral. So here is what the integral is, and that is what we are going to see in the next slide. Maybe before going there, let us change the function. So just in case you think I am doing this for some special function, let us change the function to some other function that that you might feel is more interesting. So here is your function, and let us change our x values so that we have this in a region where we can actually see what is happening. Okay, so here, so suppose I want to do it between x is 0 and 2, I want to compute this. So now we can see our various sums. So this is the trapezoidal sum. You can see it is very closely approximating the area, even with 15 many things. So here is with n is 3. So even for 3, the trapezoidal sum is very close. The true area is 8.67, the trapezoidal sum is 8.81. Let us do the left hand sum instead. So here is the left hand sum, still fairly close, and if you play this, yeah, you can see it is getting better and better and better, and it is quite close already. And here is your midpoint sum, again quite close. Here is the right hand sum, and here are your lower and upper sums. I highly encourage you to go to GeoGebra and play around with the Riemann sums to get a hang of what we are going to see next. Okay, so let us go to the next slide, which will tell us what is the integral of a function. Now the title says the definite integral. The reason it says definite integral is because there is something else called the indefinite integral, which we are going to see in the next video. Okay, so what is a definite integral? So let f be a function from D to R for some domain D. Suppose the interval a b is in the domain D, same as what we had in the previous slide. The definite integral of f from a to b. So if I say from a to b, I need not use the word definite integral, but if I do not use from a to b, then I better say definite integral to indicate that it is over some interval. So this is defined as you take the limit over these Riemann sums and you allow your the norm of your partition to shrink to 0. So limit norm p tends to 0, s of p, which is the same as limit norm p tends to 0, summation I is equal to 1 through n f of x I star times delta x I. So we have seen already this idea in the animation we had, where the number of intervals were increasing. In other words, the interval sizes were decreasing, and the interval sizes are exactly being kept track of by this norm p. So this is denoted by integral a to b f of x dx. I want to warn you that this dx is very crucial. If you drop the dx, you may run into trouble somewhere else. So I'll qualify that when I get there in the next or the next video. Okay. So if f is positive and it is a piecewise continuous function on this interval a to b, then the area under the graph of that function above the interval a comma b is measured by this integral a to b f of x dx. So if f is piecewise continuous, which means you allow some discontinuities, maybe at finitely many points, then this integral meaning the limit indeed computes your area. That is what we have seen in the examples. And if f is negative, we have to qualify that as well, because remember that the definition that we have made never assumed that f is positive or negative, it held for any function. So if f is negative, what does this number tell you? Well, that is also the area, but it is the area above the graph below the interval a comma b. Unfortunately, this number will then compute in something which is negative, because f of x I star will be negative, so the sum will be negative. So you have to qualify that with a minus. So you have to put a minus. So if you take minus of the integral, that will indeed be the area. So in other words, what the integral really computes is signed area. Okay. So if we go back to our example from here, and we, let's say I choose a different interval, let's say I choose the interval here. So, x is let's say -2 to 2, and if I compute what is the integral, you can see it is computing this area minus this area, okay, that is what it is computing. Okay, so, keep that in mind when you use an integral to compute area. Great. So, now we have a way to compute integrals or rather compute areas based on integrals. Let us do this example just to fix ideas. So, this is the example, this is an easy example. So, this is the graph of the function. So, this is y is 2x minus 1, or f of x is 2x minus 1, y is 2x minus 1 is this line. So, this is the graph of f, the red thing here, and let us say I want to compute the area between 1 and 2. Now, this is the simplest area I would want to do. In fact, I can read off from the figure here what the area is. So, if I want to compute this area, let us first ask what is the area. Well, you have this part here and you have this part here, and you can work out what the area is. So, you have a square of size 1 and then you have a triangle with base 1 and height 2. So, 2 times 1 times half, so which is 1. So, 1 plus 1 is 2. So, this area is 2 square units. Okay. Now, let us try to do this from first principles using the Riemann sums. So, let us take a set of partitions, I will call it Pn. So, what is Pn? Pn is the set of partitions 1 plus I by n. So, you have, so in other words what I am saying is x0 is 1, x1 is 1 plus 1 by n, x2 is 1 plus 2 by n, and so on. So, in general you have xi is 1 plus I by n, and so you will have x naught is 1, or rather 1 is x naught is less than x1 is less than x2 all the way up to xn which is 1 plus n by n. So, this is 1 plus I by n, just in case that was not visible. So, this is 1 plus n by n, which is 2. Okay. So, I am dividing my interval into n equal parts, the interval 1 comma 2 I am dividing into n equal parts. So, each part has size 1 by n. So, delta xi is 1 by n, and so norm p is also going to be 1 by n, and then we will allow n to go to infinity. So, norm p will go to 0. Fine. So, what do we choose as our xi star? Let us say I choose xi star to be 1 plus 1 by n, so which is xi. So, let us say we do the right hand sums. Okay. So, let us write down what this Riemann sum is. So, the Riemann sum corresponding to Pn is going to be summation I is equal to 1 through n f of xi star times delta xi. Okay. So, I will continue over here. So, what does this give us? This gives us summation I is equal to 1 through n f of xi star, but xi star is 1 plus 1 by n, and f is 2 times x minus 1. So, this is 2 times 1 plus 1 by n minus 1, that is the value of f of xi star, and times delta xi, which is 1 by n. Well, let us see what we get. So, if I simplify the things in the bracket, I have 2 plus 2 by n minus 1. So, this is 2 minus 1 is 1. So, 1 plus 1 by n times 1 by n, and I have made a mistake, of course, because this is not xi star is xi, which is 1 plus I by n and not 1 by n. So, my bad. So, this is, excuse me, 1 plus I by n, and so I should have here 1 plus I by n, 1 plus I by n, and this should be 1 plus 2 times I by n times 1 by n. Okay, I think now we are okay. So, I have two sums here. So, summation I is 1 through n 1 by n plus 2 by well, that's inside the sum, summation I is 1 through n, 2 times I by n squared. Okay, now I think you can see this and feel somewhat familiar. Let me continue over here. So, the first sum is summation I is 1 through n, 1 by n. 1 by n is constant, so it comes out, and then sum. So, you have summation over 1 which is n, so n by n which is 1. So, the first sum gives you a 1. The second sum 2 by n squared is constant, and what you get is I is 1 through n I, but this is something we know. So, summation over I from I is 1 through n, this is a formula that you may have learnt before. This is n times n plus 1 by 2, right. And so, what we get is this is 1 plus, so the 2 and 2 cancel, n and n cancel, n plus 1 by n, which is I can rewrite as, so I can take again divide it into two parts, n by n plus 1 by n, n by n is 1. So, this is 2 plus 1 by n. So, this is the Riemann sum corresponding to this partition P n, and now of course, if we let n tend to infinity, which is the same as saying allow P n to go to 0, that is the same as letting n tend to infinity, 2 plus 1 by n, and that is indeed 2. Okay, so, this is what we so we had already computed by observation that this was 2 square units, and this rather complicated computation gave us the same thing. So, I hope both the idea of what is the Riemann sum, what is the integral which is defined as this limit, and the fact that it matches with what our intuition is clear. Now, the main problem, as you might be able to see, is even for a simple function like a linear function, this was a fairly non-trivial computation to compute actually what this limit is and find it. So, if you have a difficult function, let us say like the functions we were looking at, say e to the power minus x, or some polynomial like x cube minus 2x square plus 5, if we try to use this method, it is going to be really difficult to compute what happens. You can, but it is not going to be an easy process. So, we need a way to compute this integral in a more efficient manner, and indeed that is what we will see in the next video. Thank you.